Previously, we have done with heat equation, all right, and then wave equation. There are two methods in solving wave. We can use D'Alembert for infinite boundaries, and still we are going to use MSV for solving wave equation of PDE. Okay, so our next step here, still focusing on MSV, same process, but for Laplace equation. Remember, we have heat equation, wave equation, Laplace equation for 1D, 2D, and 3D. So the solution of all of these types of PDE, okay, whether we use MSV or D'Alembert, but for D'Alembert, it is only for M wave and infinite boundaries. Okay, so now how can we solve Laplace by using MSV? Same process. So first you have to take a look at the given function. Where the given function involve what? Involve del squared U del squared u del x squared and del squared u del y squared. Okay, so it involves u, x, and y. So of course, we are going to have our expected solution in terms of what? One, our expected solution is in terms of u, x, y. Okay, so we always start with the expected solution where we are going to find u, x, y. Okay, our u should consist of u should consist of x and y, so it involves x function and y function. Okay, and then of course, first step you reduce to ODE. Okay, and then you convert the boundary condition given and so on. Okay, let's do this together. All right, so now, so from the PDE given, okay, so from the PDE given, we should have del squared u del x squared. Del squared u del x squared, del squared u del y squared equals to 0. So we should have u x x and u y y. So here x double prime and x y double prime. So substitute to the given PDE. So we should have x double prime y plus x y double prime equals to 0. So rearrange, we should have x double prime over x equals to, okay, before that, x double prime y equals to negative xy double prime. So x double prime over x equals to negative y double prime over y. And these two equations are equal when there exists a constant of lambda. So we can separate the function, the PDE here to the ODE by using the lambda obtained there. So now we have our case. Okay. All right. So here is a PDE. Now it is reduced to this ODE. Okay. So from the given problem of Laplace, now we are going to use these two ODEs to find a solution. Okay. So the Laplace equation is subject to certain boundary condition. Okay, so you can see that the equation has no dependence on time. There is no time involved, only x and y. So just the partial variables x and y. Then this means that Laplace equation describes steady state situation where no time involved. It is steady state situation. So steady state situation such as steady state temperature, stress, potential, and so on. So this kind of problem not involving time variable. All right. Okay, so for this example, a square plate is bounded by x0, x equals to a, y equals to 0, y equals to a, and apply the Laplace equation. So we have our Laplace equation here to determine the potential distribution. So we want to have uxy over the plate subject to the following boundary conditions. So you are given the boundary conditions here. So now you have reduced already. So our first step here, reduce already to ODE. So our next step is to obtain the boundary condition. Okay. So what are the boundary conditions involved for this problem? All right. Now, second step, boundary condition. So we have here u0y equals to 0. So u0y equals to 0. Okay. When x equals to 0, u equals to 0. So from the expected solution, we have uxy equals to x and y. Now, when x 0, u is 0. So x 0, u is 0. So putting y to the right hand side, we have x 0 equals to 0. Okay. And then second condition, uay equals to 0. So uay equals to 0 when x equals to a. Right? When x equals to a, y is 0. Putting y to the right hand side, we have xa equals to 0. Okay. Another one, ux0. So ux0 equals to 0. Now x is x, y is 0 equals to 0. Okay, so we have what? Can we have y equals to 0 here? Okay, so now we have how many conditions are here? So 1, 2, 3 conditions. All right? Okay, clear? Then the condition, let's use it for the initial condition later on. Okay, because we have a constant u not there. Okay, next. What is our next step? Okay, so you need to consider all cases. It's quite long, but once you got the pattern, you can do it. Okay, so our first case, lambda is 0. When lambda is 0, then x double prime equals to 0 will give you m squared equals to 0, m1, m2 both are 0. So these are real and equal. So we have x equals to e to the power of 0 a plus bx. Okay, so when x is 0, x0 equals to 0. Okay, so we have what? A equals to 0. Okay, and then when a equals to 0 now, our solution becomes x equals to bx. Then apply the second condition when x equals to a. So b equals to 0. Then a and b are 0. So we'll give you what? X equals to 0. So we put no interest. Can you see the screen? Okay, so we put no interest when we obtain zero solution. So when x is 0, remember our expected solution is x and y, right? So when x is 0, then y will be 0 also. So u will be 0. So we put no interest, no need to proceed with the second equation here with y. So proceed with the second case. Okay. Lambda greater than 0. So when lambda greater than 0, now we have lambda equals to p squared. So when lambda greater than 0, your x double prime minus lambda x now minus p squared x equals to 0. Okay, m squared equals to m squared minus p squared equals to 0 will give you m plus minus p. All right. Now we have real and distinct. So we have x equals to AE px plus BE minus px. Okay. Applying the condition, when x equals to 0, okay, when x equals to 0, x0 equals to 0. So a plus b equals to 0, right? B equals to negative a. And then we have the updated equation will become a e px minus e minus px. All right? Are you following? Okay. Now, apply the second condition. The second condition gives you xa equals to 0. So substitute x with a. We have a EPA minus E minus PA equals to 0. So from here, we can know that A is 0. So when A is 0, B equals to negative A, then X is 0. Also, we put no interest in such solution. Okay, clear? Up to this point, I think everyone can do it up to this point, right? Reducing to ODE, change the boundary condition for ODE part, and then consider all cases. Okay, next, proceed with the third cases. And then the third cases is lambda less than 0. So lambda is negative p squared. Now, your ODE becomes x double prime plus p squared x is equals to 0. Will give you m squared plus p squared equals to 0. Then your m is plus minus pi. So your x should be a cos px plus b sine px. So all of this knowledge comes from chapter 1, comes from chapter 2, right? You have obtained the types of roots and then identify the solution of each types of the roots there. Okay, so now once you obtain the solution, you can apply the condition where the condition, same condition, okay, so same condition used in each cases. So first x0 equals to 0. So when x is 0, cos 0 is 1, sin 0 is 0. So a equals to 0, right? So when a is 0, then the updated solution should be b sine px. Okay, now you have a is 0, then the updated solution now becomes x equals to b sine px. Okay, then x a equals to 0. So substitute B sine PA equals to 0. Okay, so from this, can B equals to 0 or not? You can simply put sine PA to the right and then you get B equals to 0, right? But can this B equal to 0 or not? Why? Why cannot? Yes, of course, we didn't know the value, but if you choose B equals to 0, then we will have no interest also for this case. Then what's the point? We want to find the solution, right? Because case 1, case 2 has no solution, so we have to make sure that this P cannot be 0, then we choose sine PA. So B cannot be 0, then sine PA equals to 0. All right, and sine n pi is also equals to 0. So PA equals to n pi and P equals to n pi over A. All right, so now you have your P, and then at least you know the value of the constant P, then you know the function of x, B sine n pi x over A. Okay, so you have your x, then you can proceed your y. Okay, your y, x, y double prime minus p squared y equals to 0. So m squared minus p squared equals to 0 will give you plus minus p. So real and distinct. Then y equals to AEPY plus BE minus EY. All right. So again, apply the condition. Apply the condition. So we have, what is the condition of y? Y0 equals to 0, right? So this is the condition of y. So y0 equals to 0 when y is 0. So a plus b equals to 0, right? Will give you b equals to negative a. And same process, now your y is a epy minus e minus py. Okay, because we only have one condition of y, then we just substitute what is your p there. So y equals to a e and phi over a y minus e minus n pi over a y. So this is your x, this is your y. Then uxy equals to x times y. Okay, and as you can see, there involve apa ni? Okay, sorry, I don't know what happened. All right, so now your uxy here is in terms of x and y. Then substitute what is your x and what is your y. And as you can see, your x and y both involve with n. Okay, a sequence. Okay, then your u now becomes u and xy. X is dn sine n pi x over a. Okay, and then y is a n exponent n pi y over a minus exponent minus n pi y over a. Okay, and this is a constant, this is a constant, then we just can combine un xy equals to an sine n pi x over a times exponent n pi y over a minus exponent minus n pi y over a, where an equals to an times n. Okay, up to this point. Are we good? Where we get the last two equation? The last two equation? You mean this one? The green one? This one, you have your x, okay? You have your y. And remember, our expected solution should always fulfill uxy equals to x times y. Then you just combine uxy equals to x times y. And as you can see from x and y here, there involve n, a sequence, then you just put b here with bn. So now u now becomes un sine n pi x over a, and y is a, now becomes an exponent n pi y over a and minus n pi y over a. Okay, so we combine these two constants as an. Then we have an here. Then we rewrite again the whole expression. Okay, so as you can see, case 1 will give you what? Case 1 will give you no interest. So this is the answer for case 1. This is the answer for case 2. Now this is the answer for case 3. And our next step is to combine all cases, right? So combine all cases. Uxy now is the total of u from case 1 plus u from case 2 plus u from case 3, and both u case 1 and case 2 has no interest, then we just put the summation of this. Summation from n equals to 1 to infinity of an sine n pi x over a exponent n pi y over a minus exponent minus n pi y over a. So this is your u xy. Okay? Clear? Okay, next, apply the condition given. So we have two conditions here of initial condition, but you have used this as your boundary condition. Actually, no need for this one, right? So we just focus on these two equation, two condition. ux0 and uxa. All right. Now, when y equals to 0, ux0 equals to 0. Okay, so we put 0 here. This one is 1 minus 1, 0. So this is 0, so we cannot use this. Okay, that's why we used this condition earlier. All right, so usually we use these two conditions only, right? Involve only x. But now, as you can see, y here involved with twice differentiation. So that's why we have to have at least one condition for y. So that's why we use this for condition of y. Okay, before this, we just involve with first derivative of t. Okay, now we have up to second derivative of y double prime here. So we have to have at least one condition. So we use this, and we choose this because this is simpler compared to the next one, right? So we can use uxa here as your initial condition now. So uxa equals to u naught sine pi x over a plus 2 sine 2 pi x over a, right? Sine pi x to sine 2 pi x. Okay. Then substitute your y should equals to a. Okay. Now it is equals to u becomes u naught sine pi x over a plus 2 sine 2 pi x over a. This is your u equals to summation a n sine n pi x over a. Okay, and your y here becomes a, right? So a over a becomes exponent n pi minus exponent minus n pi. Is that clear? For the second condition here? Where is n? Which n? Which n? N pi x over n pi x. This one? In uxa, you mean this one? This is the condition given based on the question. This one. This is the condition given. No n here. Okay. uxa equals to this expression. So uxa equals to this expression. So when when y equals to a, u equals to this. From the solution that you obtain, uxa, this is your uxa. By substitute y here with a. Okay, y here with a. All right, understand? Okay, so now we can reduce this function again. All right, so this is exponent, this is an. Okay, now we can change this exponent to hyperbolic function. This is minus, so sin n pi should be exponent n pi minus exponent minus n pi over 2. So if we put sin here, it means there is over 2 there. So in order to eliminate that over 2 there, this should be 2an, right? Is it? So if we substitute again, 2an sine n pi x over a, exponent n pi minus n pi over 2, we can have again, right? Okay, so if we put 2 here, and if we again change this to exponent n pi minus exponent minus n pi over 2, we can have the same expression again. So we change this exponent to hyperbolic in order to simplify the function. So now this 2an, okay, this 2an can be simplified to another constant. Okay, clear now? Anyone else question? Okay, clear, right. Okay, now, as you can see, yes, where Bn equals to 2an. Okay, so as you can see here, there is a summation involved, right? So now we want to compare left-hand side and right-hand side. Okay, so in left-hand side, it is u naught sine pi x over a plus 2u naught sine 2 pi x over a. Okay, so now u naught sine pi x over a plus 2u naught sine 2 pi x over a equals to, this is summation from n equals to 1 to infinity, right? So equals to b1 sine n pi x over a, n is 1, sine pi x over a sine x. When we substitute n with 1, so n here is 1, n here is 1, okay, this one, this n. So b1 sine n pi x now becomes sine pi x over a, and this one is sine pi, okay, sorry, pi, right? Since this is summation, plus with b2 sine 2 pi x over a sine 2 pi. Okay, are you following this? Understand or not? Let's- This is n equals to 2. Okay, now, since this is summation, it can be up to B3, B4, until n equals to infinity. But we want to make a comparison, left-hand side and right-hand side, and there are only two expressions. So we just stop at n equals to 2. Okay, so now we make a comparison. So as you can see, u0 sine pi x over a equals to b1 sine pi x over a sine pi. Okay? Okay? So b1 equals to what? What is b1? This is sine pi x, this is sine pi x. So b1 equals to u0 over sine pi. Right? Am I right? Okay, then look at the second expression. 2u0 sine 2 pi x over a equals to b2 sine 2 pi x over a sine 2 pi. Okay, what is b2? So b2 equals to, this one, 2u0 over sine 2 pi. Okay, good. Understand? Our purpose of applying the condition is to find the rest of the constant because we want to have particular solution. So now we have up B1 up to B2. So just substitute to the general solution that you obtained. So this is the general solution that you obtained earlier, right? This one. So uxy equals to summation n equals to 1 to infinity an sine n pi x over a times exponent n pi y over a minus exponent minus n pi y over a. Right? Okay. And an and bn equals to 2an. So what is your an? Alright, here bn is equals to 2an. So an equals to bn over 2, right? Sine n pi x over a times exponent n pi y over a minus exponent minus n pi y over a. Okay. And we have here, applying the condition, we have B1 and B2. Right. So applying the condition, so we have B1 and B2, then just substitute what is your B1 and B2. Okay, no need to find up to Bn because we just make a comparison up until B1 and B2. So just stop. So with this summation, just stop with what? B1 over 2. Sorry, no summation. Plus B2 over 2. So this is your U, X, Y. Then just substitute what is your B1 here, what is your B2 here. Is that clear or not? Anyone has question? Okay. Then you can simplify and factorize after this. So this is your final answer. I don't know what's wrong with my OneNote. It is automatically closed. Can you see it? Can you see the screen? Okay. How about now? Right. So basically, this is the solution for Laplace equation. All right. Any question? Okay. Right. Right, good. So now you understand how to apply MSV for all cases of heat, wave, and Laplace. Okay, don't worry. Usually it's only up to second order. Okay, up to Laplace second order. We have heat equation before this, right? We have wave equation. We have now Laplace. So the maximum order for PDE should be second order for your case. Okay, so as you can see, all of the types of PDE that we have used can use MSV, but only one type of wave, which is for infinite, can use the D'Alembert method. So that's it for PDE chapter. Is that clear? From 1 to 10, where are you for this topic? Our last topic, our last chapter here. And as you can see, it is not always about Fourier series. Okay, you have to understand once you apply the initial condition, check the expression. Is it compatible with the Fourier series? Then you can proceed with comparing to the Fourier series. But for this case, it is not compatible because the given condition itself can be used. So you can directly find the constant from the condition given. No need to compare with the Fourier series, just like we did previously. So you have to understand the expression that you obtain at the general solution before you can apply the condition and then proceed with finding the rest of the constant. All right, is that clear?